So the first exercise will be about the properties of the systems. We already know the linearity and time invariance from previous weeks, but recently you learned about stability, memory or memoryless, and then causality of the system. So now we'll try to examine those systems for all of the properties that we know. So exercise 1 or example 1. Let's say we have a system with this output, yt equals xt minus 3 plus x4 minus t. Memoryless, stable, causal, linear, or time invariant. Let's start checking each of those properties one by one. Let's start by the memory. So is this system memoryless or it has a memory? Anyone? Anyone want to answer this? You can just unmute yourself if you want to answer. Okay, I'll just solve it myself. Please just unmute yourself anytime and ask.
I don't think we were taught about memoryless yet, or at least like from I'm looking at my notes right now. It's empty. I think he skipped that part and
Uh,
just
so you didn't talk about just the memoryless or all of them?
like we went to causality, and then he skipped memoryless and went straight to stability.
Okay, okay. I'll explain this one. I'm not sure. I don't think you're supposed to know it, but I mean, I'm not sure if you will be asked to 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 check those properties or the memoryless property in the exam, or if you didn't take it in the class. But I'm sure the professor will cover this one later. So I'll quickly explain it and then solve this part, and then we'll continue. So a memoryless system is simply a system that to produce an output for the current time step, it needs just the current time steps or the previous time steps. In other words, it just needs sorry. A memoryless system, in order to produce an output at the current time, it only needs input at the current time. Is that clear? So to produce yt, it needs x at time t only, nothing else. So this system is clearly not memoryless because it depends on t minus 3, 4 minus t. So not only t, not only the current time steps, the current time. It requires some knowledge about the past and also the future, this system. So it's not memoryless. In order to get y, we need to store this value from the past, and also it needs some values from the future. So this is not memoryless. So this system has memory, as it depend on past and future inputs. So in order for a system to be memoryless, it should depend only on the current input, not the future and not the past.
Does time reversal count or no?
Yeah, I have already taken this into account.
Oh, sorry.
Yeah, and if t, let's say if t is less than 4, let's say t equals 1. When t equals 1, so we have then we have y1 equals x minus 2 plus x 3, right? So this one is in future, and this one is in the past. Yeah, and this part is because of the time reversal and time shift, and this one is just time shift. So yeah, so it needs memory to store those past values and future values. So it's not memoryless. It has a memory. The next property is stability. How do we check if a system is stable or not?
Is it if the input depends on only present and past values?
No, that's actually the definition of causality.
Oh, that's right. My
That's a
bad.
causal system. Yeah. Stability is about like from the word itself, a stable system should not explode, let's say. So if you give it an input that's bounded, should give you an output that's bounded. Shouldn't explode. The value should not explode. Like it gives me infinity for a finite input. So a stable system will produce a finite output when the input is finite or bounded. So the definition was if xt is bounded by some m, let's call it mx is just some finite value, not infinity, then the output will be bounded by some other value, finite value. So from this definition, to check if this system is stable or not, we need to first assume that the input is bounded, and then we need to check if the output will be bounded or not. So first, let's assume that xt is bounded. Let xt is bounded by mx. Then we have here two versions of this xt. One of them shifted to the right, the other one reversed and shifted to the right. Time reversed and shifted to the right. Are those bounded? If xt is bounded, xt minus 3 will be bounded or not? It will be bounded because let's say xt was some signal like this. And then if we do time shift, it will be the same signal, but let's say here. Let's say this is 3. So xt minus 3. So if xt is bounded, then time shifting or time reversing will keep the signal bounded. So xt minus 3 is bounded and x4 minus 3 is bounded by some value, say alpha and beta. Then
Isn't that 4 minus t?
4 minus t, yeah, that's great. Thank you.
Mhm.
Yeah. So doing time shift or time reversal will not affect the fact that the signal is bounded. Now, yt is the summation of those two. So we have a bounded quantity, the first bounded quantity, which is xt minus 3, plus the second bounded quantity, which is x4 minus t. Then the summation will be also bounded by alpha plus beta. So the system, this is let me correct. It's not accurate. So we need to check if yt is bounded, and yt is xt minus 3 plus x4 minus t. And this is less than or equal xt minus 3 plus x4 minus t. Do you know which inequality did we use to move from here to here? This is called the triangular inequality. If you have a plus b, absolute value is less than or equal a plus b. So this is bounded by the first term absolute value plus the second term absolute value, which is less than or equal alpha plus beta. Then the system is stable because yt is bounded by some finite value. Let's call this my, and it's less than infinity. It's finite. So the system is stable. The next property is the causality. So I think there's an I here. I'm not sure. From the definition, the causal system depends only on the past, not the future. And if we look at this output of the system, we can see that it depends on the future from this term. It depends on the future. And as from this example that we have seen, let's say when t equals 1, then y1 equals x minus 2 plus x3. And x3 is in the future. As we are looking at the output at time 1, time 3 is the future. So this system is not causal. It depends on future. And it's not causal. The last two properties, the linearity and time invariance, I think you have practiced those a lot. Those are not new, but the other properties are new. I'll just write the definition of those two properties just to remind you of, and then I leave it for you to check if the system is linear or time invariant. So a linear system, if we have a linear system, then if we input to the system x1, let's say also scaled x1 and scaled x2, the output of this system will be just a scaled output if we inputted the first signal alone plus scaled output when we use x2 alone as the input. So x1 t will give me y1 t, x2 t give me y2 t, and then if I do this linear combination of x1 and x2, the output will be a linear combination of y1 and y2. Sorry. So if this property is satisfied, then this system is linear. Next is this is the time invariance. A time invariant system will show if we shift the input, the output of the system will be shifted with the same time shift. So if xt as input will produce yt as an output, then if the system is time invariant, then xt minus t0 will produce yt minus t0, with the same time shift. So if this is satisfied, then the system will be time invariant. Please check those properties as an exercise for this example. And we'll move to another example. Let's say example 2, yt equals cosine 5t times xt. Again, we want to check if this system is memoryless, stable, causal, linear, or time invariant. Starting from the memoryless property. Is this system memoryless based on the definition that I have explained?
Yeah, it is, because it only depends on the input time.
Yeah, that's correct. Thank you.
Yep.
Yeah, it is memoryless because it just depends on t, on the current time. It doesn't need, like, if we want to implement this system in hardware, we don't need to use any buffers or any memory to save the input before producing the output. We can directly use the input to produce the output without any memory in between or any buffering. So this system is memoryless. It doesn't need any memory. So it is memoryless. Then the stability. Is it stable?
Yeah, it's still stable because it only depends on the present and it doesn't have a past or future in the function.
You are confusing with the causality.
Oh,
Yeah.
right. Okay. My
Yeah,
bad.
that's the causality, but the stability is about, as I said, about a stable system doesn't explode. If you input something finite, the output should be something finite. Nothing grow infinitely till infinity. So to check if this is stable, as you said, we should first assume that the input is bounded or finite. So let xt is bounded by some m, and then we need to check if yt is bounded, equals cosine 5t xt, which is bounded by cosine 5t mx, and this should be also right. And then how can we bound this function? What's the upper bound of this function? Cosine.
Is it 1?
It's 1. Yeah, that's correct. So it's bounded by minus plus 1. So it's 1. It's cosine. This is less than or equal 1. So yt will be bounded by mx. And this system is stable. Now the causality. Is it causal?
Yeah, it is.
Yep. Because it doesn't depend on the future. And there's one note: if a system is memoryless, then it will always be causal, right? Because a memoryless system doesn't depend on future or on the past. So it will always be causal. Like memoryless condition is more strict than causality condition. If it's memoryless, then yes, it's causal, but not the other way around. And yes, it's causal. Or let's say the output does not depend on the past. And next will be linearity and time invariance. Can you tell if this system is linear or not without doing the calculations? Let's check it. Let's assume we have input x1t, then the output will be from the definition of the system, or the output of the system, it will be cosine 5t x1t. And if we have another input x2t, the output similarly will be cosine 5t x2t.
I have a quick question. For causal, isn't it that the output doesn't depend on the future, but only the present and past?
Yeah,
Or
you're right.
okay, yeah,
Yeah, thank you. This is the anti-causal.
Yeah.
It actually shouldn't depend on the future. But yeah, this system is causal, but the writing here is not correct. The output doesn't depend on the future. It only depends on the present and the past. Yeah, thank you. So for the linearity, we have two inputs and we have their outputs. We'll call this one y1 and we'll y1t. And this one, we'll call it y2t. Now, if we construct a new input, we'll call it xt, which is just a linear combination of those two inputs, alpha x1t plus beta x2t. And we will use this new input or this new signal as an input to this system, and we'll check what the output will be. Then yt will be cosine 5t times alpha x1t plus beta x2t. And this will be cosine 5t. Let's keep the alpha here outside. x1t plus beta cosine 5t x2t. And this is alpha y1t plus beta y2t. And the system is linear. This system is linear. The time invariance, first here, call it linear, then time invariance. To check if the system is time invariant or not, again, we start from a signal. Let's say we have x1t. This will produce an output equals cosine 5t x1t. Now, assume that we have another signal is just the same x1t but shifted. So this new signal is the same as the previous signal but shifted by t0. And we apply it as an input for this system. The output will be, so we should call this one y1t. Let's call this x2. x2t is just x1 shifted, time shifted. The output will be for this new signal as an input to the system. We get this output, which is cosine 5t x2t. And x2t is just x1t minus t0, so cosine 5t x1 t minus t0. Okay. Now we have the output when the input is time shifted. We need to tell if this system is time invariant. we need to check if this one is the same as this one, but time shifted. So the procedure here is just do a time shift on the input and calculate the output, and then do a time shift on the output and compare those two outputs. If they are the same, then the system is time invariant. What we are saying is that, let's say the input is some signal that looks like this, and we use it as an input to some system. The output will, let's say the output will look like this, for example. If this system is time invariant, then if we shift this signal, let's say we make it like this, assume that those are identical, but just time shifted, T0, and we use it as an input, the output should be the same as the previous output, but just time shifted. Again, assume that those are identical. The only difference is just the time shift. So here we have T0. So if the system behavior is like this, then we say this system is time invariant. And this is what we are trying to do here. We had an input-output relation. We shifted the input and observed the output. Then we shift this output and compare it with what we have got. If they are the same, then the system is time invariant. Now, let's write this y1 t minus t0.
I have a quick question. So when we're shifting it, so in y2 of t above, do we have to do a 5t minus t naught, or for the inside the cosine?
We should, yeah, because what we are doing here is just substituting for, instead of each t and every t minus t0, t naught. So yes, you should do it everywhere.
Okay, I was just confused because like the one you wrote, it didn't have it, so I wasn't sure if we're doing it afterwards or
here, yeah, that's a good point. Be careful. Yeah, here we are just shifting xt.
okay.
So just the x part of the output is getting affected, right? Here, if you compare it with this system, when we give it x1t, it gives us cosine 5t and the same multiplied by the same input, right? If we do any modification on this x, the only part that will be affected is this one. This one is just part of the system. If we modify the input, this should not be modified. It should not be affected.
Oh, okay. That makes sense.
Yeah.
Thank
So
you.
we shifted the input, the output will be affected just in this part.
Okay.
Yeah. But yeah, but here I'm shifting the output itself, right? Here we are, like, after we got the output, we are shifting it. So we are replacing every t in this y1t by t minus t naught. Not only x1, because we are shifting the whole output, not
Okay.
just yeah.
All right. Thank you.
Yeah, no worries. So now we'll have x cosine 5 t minus t naught times x1 t minus t naught. And we can see that this is different, and this. Those are not the same. Those are not the same. We have this extra term here. So the system is not time invariant. is, we can say time variant or not time invariant. So it is time variant. So when we shift the input, the output will be shifted differently because the system is not time invariant. If the input shifted by t0, this is not correct in this system. It will be shifted differently, not by t0. Yeah. Let's do one last example on the properties of the systems before moving to the convolutions. Let's do one discrete time. I think we are at example 3 now. Let's say we have a system, the output of a system is yn equals summation k equals minus infinity to 2n xk. And we need to check if this system is memoryless, causal, stable, linear, or time invariant. Is this system memoryless? Again, a memoryless system should not depend on any other time instances other than the present. So the present here is n. Is the system memoryless?
Is it not memoryless because it's like a factor of n instead of just n?
Yeah, that's correct. It is not memoryless. It has memory.
Yeah.
Because let's say for n equals 1, we have the summation even regardless of even if this is just n here, even if this is n here, but we are adding all the terms from minus infinity till n, or in this case 2n of the input. So it has memory, or it needs memory, or it's not memoryless. Because even at n equals 1 or any value, we are summing, we have a summation over all xk's from minus infinity till n or 2n. So it depends on other time instances other than the present, other than n. So it depends on n minus 1, n minus 2 until minus infinity, and also until 2n. So it's not memoryless. The condition here to check is is if it depends on future or on the past. But in our example here, it depends. It's depending on both, so it's not memoryless. But one of them is just sufficient to say it's not memoryless if it depends on future or on the past.
Is it by future because there are negative k values?
No, the negative k values are part of the past.
Mhm.
Yeah, because here, let's say n equals 5. So y5 equals x minus infinity plus many terms in the past, and then we reach x 0 plus x1, and then plus until x10. From here, from x5 here, somewhere here, we have the x5. From here and after this point, we have the future, and before this point is the dependence on the past. So yeah, so this system depends on both past and future. Okay. Is this system stable?
No, because it's unbounded in the negative, like it goes all the way from negative infinity.
Right. Because even if xk is bounded, this summation will not be bounded. In general, yeah, in general, it's not stable. It actually depends. If xk is less than or equal 1, strictly less than 1, then it will be stable, right? Because this summation will confer, I'm trying to compare it with the geometric series. Let's say we have k equals minus infinity to some value to n, then r to the k. For this series to converge, the condition is that r is bounded by 1, right? But this is different. But yeah, I think this depends. There will be some condition where this system will be stable, and otherwise it will be not stable. If we bound this the input by some strict bound, it will be we'll find a condition where to make this stable. Because this xk can be written as rk, r to the power k. And if r is bounded, then this will converge. And this actually is the same. It will become a geometric series, right? And it will converge. And if when I say it converges, it means that this summation will be less than infinity. It will be bounded. So this system you cannot tell in general if it will be stable or not, depending on the xk. So it can be stable and it can be not stable. But think about it yourself, and I will post the solution for it later on after I review it in a better way. And I don't want to lose the time currently because we still have only 30 minutes or so. Think about this one, but consider what I said here is just as a hint. There should be a condition that will make the system stable. Otherwise, the system will be unstable. But I'll post the solution for this one on the canvas, or I'll send it to the professor and he will post it. Let me just write it here. Next is about causal. Is it causal?
Yeah, it is, because it only depends on all the past values and the present value. It doesn't reference the future.
But this 2n,
Oh, like in the end, for the last value,
yeah, it can
it
go
does.
to the
Okay, okay.
the future values. Yeah. So if n equals 1, this will be function of 2, or it will be function, yeah, it will be function of x2, and in addition to other terms, but x2 is what matters, which is in future.
Okay, okay, that makes sense.
Yeah. So this system is not causal because it depends on future. Let me put it here. Then linearity. And to do the same, let's assume we have input 1 xt. This will produce not t, n, produce y1 n equals k equals minus infinity till 2n x1 k. Then another input will produce, or yeah, will produce this output. Two n x2. Now, if we have a linear combination between those two inputs, and we name it, we call it xn, alpha x1n plus beta x2n. This will be the new input. So the output will be yn equals summation k equals minus infinity to 2n xk, which is summation minus infinity to n for alpha x1n plus beta x2, sorry, k, not n. Now yn equals summation k equals minus infinity to tn of alpha x1 k plus beta x2 k. Let's write alpha y1 plus beta y2 to compare it with this. But on the other hand, we have alpha y1 n plus beta y2 n equals yeah, just alpha times summation xk x1k plus beta 2n x2k. Are those the same? Hmm?
Yeah, they are the same, right? Or
I think so, because you can separate the summations, right? And since alpha and beta are constants, you can put them to the
Yeah.
front.
Yeah, that's correct. Those are the same. Yeah. So this system is linear. Time invariance. As we did before, let's assume we have x1 n will produce y1 n, which is summation from minus infinity to 2n x1 k. And then let's assume we have another signal x2 n, which is just x1 but shifted, time shifted. Then y2 n. When we write here y2 n, it means that x2 is the input. So y2 n equals minus infinity 2n x2k, which is minus infinity 2n is x1 n minus n0. Now we have the output after shifting the input. After shifting the input, we need to compare this one with the shifted output. So we need to write y1 or shift the input y1 by n0 and compare this one with this one if they are the same. So yn minus n0. So we need to shift this signal. We forget about everything happened here, x1 and the system, and we just assume that this is a signal and it's a function of n. Oh, yeah, I made a mistake here. Let's see. Here I've written n minus n0. That's not correct. So x2k, which is this is the input is shifted. y2 at n equals summation of minus infinity till 2n x2k. Here k is instead of n, then k minus n0. It will be summation minus infinity 2n of x1 k minus n0. Right? We just shifted the signal, but this summation is part of the system. We didn't shift the system. We didn't shift the output of the system. We just shifted the input by n0. Now we need to compare this one with what we get after shifting the output. Here we shifted the input and checked the output. Now we shift the output of this original signal x1. So we just shift, instead of y at n, it will be at n minus n0. So from minus infinity till 2n minus n0. Everything else remains the same. Is this system time invariant? Are those the same?
No, they don't look the same.
Yeah, that's correct. They are not the same. Because at the end, if we do the summation, you'll have terms plus the last term here will be x1 at 2n minus 20. 2n minus 2n not, sorry, in this case. But in this case, we'll have some terms, and then the last term will be x1 at 2n minus n naught. They are different. So the time shift here is different than the time shift here. Not only in this term, the other terms will be affected. No, never mind. The last term is different. So those two are different, and the system is not time invariant. It's time variant. Let's now move to the conclusions.